Okay, I'm going to do this entirely on the blackboard. So if some of you would like to come forward, that's good. But I know you can also see things there. So if that's okay, you can stay there. But if not, I'm just going to be using the blackboard. So I want to talk today about local operators in AdS CFT, and I want to say that these talks are all geared towards building up to understanding the information paradox and recent developments in the information paradox, and seeing how one can understand them using AdS CFT. I won't talk so much about the information paradox itself today. I'll do that tomorrow and then the day after. But I want to do something which is very important as paid work to understand that, which is the issue of how one tries to understand local physics in AdS CFT. Okay, so that's the thing I want to talk about today. And roughly, I'll divide my talk today into two parts. I'll talk about local operators outside a black hole in AdS CFT. So I'm going to consider a black hole in AdS CFT, and I'm going to try and talk about how you can describe local physics outside the black hole. And then I'm going to talk about local operators inside. And as I'm going to say, this part one, is something which is in some sense, at least conceptually, which has been known from the early days of AdS CFT. And I'm going to try and emphasize some of the new parts that come about when you try and describe local operators inside a black hole. Okay? And in the end, what I want to conclude with, and this is going to be an important formula, I want to conclude with an important statement, which I'm going to use then in the second and third lectures, which is what is the condition for having a smooth horizon in AdS CFT. And then tomorrow, I'll try and tell you what are the recent arguments that suggest that you don't have a smooth horizon, that this condition is not met. And then day after, and perhaps also tomorrow, I'm going to try and tell you why I disagree with those arguments and why actually you do have a smooth horizon in AdS CFT. But today, I'm just going to try and talk about these three things. Okay? So that's a rough overview of what I'm going to say. So let me.
Gautam Mandal today evening will introduce the information puzzle, and so
Okay.
So it will work in time.
Fine. Let me start by talking about local operators outside a black hole. Okay, so what do I mean by that? So this is something which is in some sense been known from the early days of AdS CFT, but isn't discussed much. So let me just try and describe that to you. Okay, so how do you usually phrase the AdS CFT correspondence? You say let's work with some metric which looks like this, okay, asymptotically. So there's a metric which asymptotically looks like AdS. It may be just empty AdS, or it may just asymptotically look like AdS. And then you have some field in AdS, and this field has some behavior, okay, which says that towards the boundary, so this field has some dimension delta, and I'm always going to be in AdS d plus 1. And this field has some behavior which says that as you go to the boundary, it takes on some values. Okay, its behavior in the z direction, the radial direction is fixed, and it takes on some boundary value, and the boundary value has some non-normalizable coefficient. Okay, and then the way you usually phrase AdS CFT is you say let's do the bulk path integral over all kinds of fields with this boundary condition. That it has the field has this kind of behavior, and this is what is supposed to be the CFT partition function, okay, but with this guy acting as a source for some dual operator. Okay, so this is the way you usually phrase AdS CFT, and the important point here is that you turn on a non-normalizable mode for for the bulk fields, and a non-normalizable mode takes on some boundary conditions at the boundary of AdS, and then those boundary conditions act like a source for something else in the CFT, and this is the usual phrasing. This is how Witten phrased the AdS CFT correspondence. Okay, but there's another way of talking about it, which is in some sense I think better and but also more unusual, which is that you can also talk about AdS CFT in terms of maybe can I erase this or do you want this or no? You can also talk about AdS CFT as giving you a relationship between just bulk and boundary correlators. Okay. As the following statement, you can think about AdS CFT as a statement that boundary correlators are boundary values of bulk correlators. Okay. Okay, so what do I mean by this? By this, I mean that you think of, you have some bulk quantum field theory, or you have a bulk string theory, but in some sense you can think of fields in that, and you compute Green's functions in this theory, and then the claim is that you have this. I'm going to be a little schizophrenic about x. So in this, when I write x here, x is a boundary direction. Okay, z will always be a radial direction. Sometimes I'll write the time coordinates separately, especially when I'm talking about things at finite temperature. It will be useful to write t separately, as I've done here. Okay, but sometimes just to avoid writing more, I'm going to just write x, and this always means t and x. Okay, so it's put these equal. Okay, what is this statement? This is the statement that you compute some bulk Green's function. Okay, you have a bulk field phi, which has some dimension. Okay, and you compute some Green's function in the bulk. Okay? Now, when you compute a Green's function in the bulk, when you quantize a field in AdS, whatever background you're quantizing it about, you always turn on only normalizable modes. Okay? You never turn on a non-normalizable mode to compute, just to deal with quantum field theory in AdS. Okay? So you compute a normalizable mode, you compute some Green's function using that. This Green's function has some die-off. Okay? It dies off as z to the delta near the boundary, because remember, you've only turned on normalizable modes, and you compute this Green's function in the bulk theory. You strip off, the leading dying off coefficient, which is this z to the delta part, and then there's some wave function normalization factor, which is capital Z. Okay, that's some wave function normalization factor, the kinds of things that usually appear in your LSZ formula. And this is capital Z to the power n, and this is small z to the power minus delta. Yeah, all of these are minus delta. I've taken them all to have the same dimension. Oh yeah, this is minus delta. Yes, there's a minus delta. So and the claim is that and then this object you compute some bulk correlation function, and the boundary value, which is a z goes to 0 value of this correlation function, is in fact a CFT correlator. Okay? So this is a direct relation between CFT correlation functions and bulk correlation functions. And in some things, for example, when you try and compute the 2-point function, there's this famous subtlety in computing the 2-point function of fields that are not marginal, which is something that worried people in the early days. Of course, you can get it using this prescription, but often it's more convenient to use this prescription. Okay? And the other advantage of this prescription is that you never deform the boundary. Okay? Even if you're computing a correlation function of gravity fluctuations, these are always normalizable gravity fluctuations. So your boundary is just sitting on flat space and is never getting deformed. Okay? So in some sense, this tells you also very clearly why you should have conformal invariance for these correlation functions. But in any case, this is an equivalent formulation of AdS CFT, which is just this, that boundary correlators are boundary values of bulk correlators. Okay, and that's the precise statement of that. Yeah, indeed. That's right. All of them go to 0 simultaneously. They can also be delta 1 to delta n, yes. Yes. You can have different things. Yeah. Right. The non-normalizable mode is what turned into boundary source. Yes. 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 That's right. You never need to turn on non-normalizable. Turning on non-normalizable modes from the point of view of the bulk theory is kind of a funny thing to do. From the point of view of the bulk theory, if you want to quantize something, you generally just quantize it by saying that the fluctuations die off at infinity, not that they. So this is, if you compute bulk Green's functions, then you just work with normalizable modes. Okay? But I mean, you can get this from this by taking derivatives of this with respect to the source. If you take derivatives of this with respect to the source, you'll pull down the left-hand side, and it requires some work, but you can show that the other thing also follows. So these things are equivalent, but this is just one convenient way to think of AdS CFT. Okay? Yeah, this equivalence can be shown within perturbation theory at least. Yeah.
Okay, thank you.
You can show this perturbatively.
Just some is little z independent, but just involves the dimension.
That's it. So this constant z is indeed little z independent. You know, it's actually it's also just a question of normalization. You know, you pick some normalization, some kinetic term for your 2-point function, and you have to pick a normalization also for. So actually, little z is also just capturing that. It's also capturing how you relatively normalize the bulk field and the boundary field. Sorry, capital Z is capturing that. Little z is just the radial direction. Yes, you could take little z to be 2z and then your capital Z will change, right?
I have a very basic questions about this normalizable and non-normalizable mode. So here you have taken this limit as z tends to 0, but in general, if I think that all these normalizable modes are falling z to the power something.
They're all falling as z to the delta.
Yeah, z to the power delta. I mean, delta can be within some parameter range.
Yes.
So, which basically means that all these fields are vanishing at infinity.
Yes.
So, which means that like the probability of finding the particles, if you like think about it, if you have some particle that has been say originated at the horizon and it is flowing there, so
Okay.
which shouldn't it give like a trivial matrix?
But you know, that's why I'm stripping off the leading die off. You know, it's true that if you just look at this Green's function, this Green's function goes to 0 as z goes to 0. But that's why I'm pulling off these leading factors, and I'm looking at the rest of it, and that coefficient is significant. That coefficient is in fact the boundary value. Okay, so it's true that the Green's function itself dies off, but that's why I pulled off the z to the minus delta factor. That's a divergent factor. Is that good? Are you happy or?
I'm still not sure. Like, I mean, if you do not take this, I mean, if you define S matrix elements in bulk, I mean.
So this is not an S matrix element. You know, there's no S matrix as you conventionally define it. This is slightly different. You know, it is a boundary value of a correlation function, but it's not what you usually call an S matrix. An S matrix, you know, in AdS is a more difficult thing to define. So this is not an S matrix. It's simply the statement that you look at the Green's function, you take its boundary value, it dies off in a particular way. You know how it dies off, and the coefficient of that is something that's interesting. Okay. Okay, good. So now the question I want to ask is, you know, given, so you know, AdS CFT tells you the boundary values of these correlation functions. It tells you that if you have some bulk fields, you know their boundary values. Okay. And conceptually, this is like an S matrix, although as I said, it's not precisely an S matrix. It's something different. But now the question I want to ask is if you can reconstruct bulk Green's functions using these boundary values. So you know the boundary values, okay, and the question is whether you can reconstruct bulk Green's functions. Okay. And in fact, there are two slightly different questions which look like they're the same, but they're not quite the same. Okay. The first question is, can we get bulk Green's functions? The second question is, you know, can we get bulk operators? That give these Green's functions. Okay. As correlators. Okay. So they're slightly different questions, as you will see when I talk about the interior, although they look like they're the same thing. Okay. But conceptually, the question is, you know, you're given the boundary values of these Green's functions, and now the question is, can you extend them into the bulk? Okay, so that's the question I want to ask. So you know, in general, of course, you know, if you're just given the boundary value, you don't expect to be able to extend things into the bulk. You're just given something. But you know, we know that, let's say we are working in some large end limit where the bulk theory has a perturbative expansion. So the bulk theory, in some sense, is approximately perturbative. In that sense, in that setting, you know that these Green's functions, and you know also that, you know, these bulk operators, these local bulk operators, they obey some equation of motion. Okay. So if you wanted to extend these boundary values into the interior, then you expect that, you know, the first thing you should do is you should look at the kinds of equations of motion that you get and try and solve those equations of motion with these boundary conditions. Okay. So that's the kind of thing that you'd like to do. So let me just try and describe that in detail. What I'm doing is conceptually simple, but that will just give you a flavor of how you do this local construction. Okay. Yes, yes, they will be gauge dependent. Yes, so these are not gauge invariant quantities. Yes. Yeah, you have to pick a gauge, of course, to construct them, because I mean, first of all, as Ashok pointed out, in gravity you don't have any gauge invariant local observables. Okay, so there are no local observables that are gauge invariant, because and the reason for that is kind of simple. You know, in some sense, everything couples. You know, gravity couples to a total energy. So if you have something that's localized in some region, it always couples, you know, to a gravitational field. So if you want to construct some gauge invariant observable, you have to you know, integrate over all of space time. Now you can do some other things. You can try and construct these things called relational observables and so on. But in the end, you know, we can also do something much simpler, which is to just work with these gauge dependent objects. Okay, and then in the end, you can try and talk about what are the gauge invariant observables you can get out of this. Yeah. Yeah. Yes. Some. Yes, yes, that's true. That's true. If you're working right, so in perturbation theory, if you're in perturbation theory in 1/n and you have some background geometry, then you can use your background geometry to set up your rods and clocks and so on, and then try and define you know, local observables with respect to that. But of course, if you put in a lot of energy, then the background geometry, huh? Right, so you can try and do it in some, in some perturbative sense. But I agree with you, of course, if you put in a lot of energy, you don't expect this to be some non-perturbatively sensible thing. But I think in perturbation theory, you can probably talk about fields I mean,
even after you include quantum corrections, you think that you can have gauge invariant objects?
Yeah, okay. I mean, you can probably.
Yeah.
There's back reaction, but you can to zeroth order you have a nice definition of invariant.
Yeah, in a zeroth order you have, but I think in perturbation theory, once you start doing loops, I'm not sure if you can get gauge invariant objects, operators.
Yeah, maybe that's right. I'm actually very happy to accept that they're gauge invariant, because I agree that you know, local observables in general shouldn't make you know, so much sense within a theory of quantum gravity.
Because even in QED, for example, the electron two-point function is not gauge invariant.
Absolutely.
Right?
So in particular, some of these fields are charged, and you try and construct something like that. That's actually something that's easier to get rid of, because if these fields are charged, you can actually attach them to the boundary with a Wilson line. So you take a Wilson line, you attach them to the boundary, and then you get something. In gravity, it's much hard. You know, if you want to make them gauge invariant with respect to gravity, that's much harder to do. But the charge, you can attach some Wilson line. Even then, they're secretly non-local operators, because they have Wilson lines that stretch from, you know, from some point in the interior to the outside. So for example, you know, as Ashok says, it's true that, you know, if some of these guys were charged, one simple way to see that they're gauge dependent is, if you look at a correlation function or a commutator of one of these guys in the interior with the charge near the boundary, that guy doesn't vanish, even though you might think that, you know, the charge is being computed at the boundary and you have a commutator that's space-like separated and should vanish, but it doesn't vanish, because these operators that you're constructing are gauge dependent, and they secretly have Wilson lines attached to them, even if you forget about the gravity bit. But this is slightly peripheral to the discussion of local operators. So, but in some sense, you know, you expect that even in a theory of gravity, even in, you know, even in QED, there's some approximate sense in which you can talk about local, you know, about local physics, and that's roughly the sense I want to make precise. But there are these subtleties that have to do with gauge dependence and so on, and those subtleties should be kept in mind at the back of your mind.
But suppose I'm doing in QED, I computed two different gauges, I put them on cell, I will get the same result, right? It's not.
If you're computing in the end a gauge invariant quantity, you get the same result. If you're computing a non-gauge invariant quantity, you won't get the same result. Now, if you look at the electron field and you compute, for example, its commutator with the charge, or you compute its commutator with the electric field, that's something that depends on how you chose the Wilson line. You know, the electron field per se is not a well-defined object. If you want to compute the commutator of the electron field in the electric field, that's not a well-defined object till you tell me how you put the Wilson line. And different ways of choosing the Wilson lines can give you different commutators. So this is, you can just check in QED, just by quantizing in different gauges, you can get different answers for this. Okay, yeah.
Sorry to just go back to this equation.
Yeah.
I mean, if I don't want to remember the first board where you given that I mean, how do you relate the boundary operators with the bulk fields? If I just
so there has to be a dictionary. Equation? There has to be a dictionary always between boundary and bulk. That dictionary always exists even in the first place. You have to say, if you want to phrase this as a correspondence between two different theories, you have to tell me that the bulk field is related to some particular boundary operator. Now that dictionary you have to write down even there.
Yeah, but so there it was through the non-normalizable mode.
Well, right, but I mean, so you know, it's always a dictionary. When the non-normalizable mode is a source for what operator in the boundary. So you always have to tell me it's a source for what operator. You have to tell me what that operator is. Okay, so you have to tell me what the duality between O and phi is. That is something you need in both cases. Okay. A dictionary you always need. Okay. Okay, good. So let me just say the following. So you know, just to set the background, also for what I'm going to do later, you know, let me think of a big black brain in AdS. Okay, so this black brain has a metric, you know, which looks as, it's a slight, you know, asymptotically it's the same metric as what I wrote before, but it's where is function h of z, okay, and the horizon is at z equal to z0, okay, and this is related to the temperature by d, where, as I said before, we are in AdS d plus 1, okay, so this is d minus 1 dimensions, okay. So this is a big black brain in AdS, and I'm going to be working in this background. At various points, especially when I start talking about the information paradox, it will be more convenient to think of a big black hole in AdS rather than a big black brain in AdS. That's just because, you know, things are discrete and for a big black hole in AdS and there are no infinite directions, but conceptually it's the same thing. Okay. So this is something which has some temperature which is of order 1. Okay, it's some temperature which is of order 1. The temperature is not, you know, the energy of this object or the energy density of this object is order n squared, or it's of order the central charge in the theory, but the temperature is something that's order 1. Okay. So I want to now ask, you know, how can you do this object, how can you do this procedure of trying to extend these boundary values into the bulk if you know that you're in a state of the theory which in the bulk corresponds to this geometry, okay, and in the boundary corresponds to some other state. So I want to do this process in that state. You can of course do this process as a starting point just in empty AdS, but you know, just because we have limited time here, I'm just going to do it directly around the big black hole, and that's conceptually almost the same thing as doing it about empty AdS. Okay. Okay. So the first question is, you know, you want to solve So the first thing, as I said, if you wanted to extend these boundary values of Green's functions into the bulk, would be to solve the wave equation. Okay. So let's say you take again a massless scalar field. This is a field which has dimension equal to dimension equal to d, where d, you know, the d is the boundary dimension. So it has delta equal to d, and I'm not putting a mass here just for simplicity. Okay. But if you think of this kind of field, even in this geometry, you can write down some solution okay, which has some planar behavior in the boundary and has some radial profile. Okay. And if you just think of this equation, this reduces to a second order differential equation for, you know, which I'll just write schematically into a second order, you know, equation for this linear differential equation for this function chi. Okay. This linear differential equation in general is something that's hard to solve analytically, although if you're in AdS3, then you can solve it in terms of hypergeometric functions. But I want to make a few statements about, you know, the existence of solutions. The first statement is that some of you might remember that in empty AdS, okay, I just want to make some statements about the existence of solutions in this background. In empty AdS, if you remember, you know, solutions exist, normalizable solutions exist only for omega squared greater than k squared. I don't know if you remember this fact, but if you try and solve if you try and look for normalizable modes in empty AdS, they exist only for this condition. They exist only for time-like modes. Okay. Now in a black hole, this is not true. Okay. So you have solutions that exist for all values of omega and k. Okay. So you give me a value of omega and k, and you can find a normalizable solution. You can find normalizable solutions even for space-like momenta on the boundary. The second statement I want to make is that the spectrum of omega is continuous. Okay. In a black brain, this is actually a trivial kind of statement. The spectrum of omega is always continuous. But once again, if you think of global AdS, you know, just about empty AdS, and you try and look for the spectrum of omega for a field of dimension delta, that spectrum is quantized. Okay. So you can't have arbitrary frequencies on the boundary in global AdS, but this is true even in global ADS. Okay. Even if you're in global ADS and you ask what are the solutions of the wave equation, and you know what are the kinds of frequencies that you're allowed about this background, then you're allowed all possible frequencies. Now that is a sign of the fact that if you think of the black hole in the boundary theory, the black hole in the boundary theory is some highly excited state with some energy of order n squared, and these fluctuations of the field are describing transitions between those energy levels, and those energy levels are very finely spaced. In fact, they have a spacing that goes like e to the minus n squared. Okay? So that's the reason why the spectrum of the Klein-Gordon equation about the black hole background gives you a continuous spectrum for omega. On the other hand, if you're about empty ADS and you have some discrete particles, you have some mass cap in global ADS, not in the black plane, but in global ADS you have some mass cap, and so you can only excite some discrete frequencies. Okay? But that's not true about the black hole background. Okay, so I just want to make these statements, general statements about these solutions. Yeah. No, I'm putting no boundary conditions, so no boundary conditions. Okay, this is important. If you put an ingoing boundary condition, then in fact you get solutions only which always have a positive imaginary part in omega, and these are the so-called quasi-normal modes. Okay. So if you put ingoing boundary conditions at the horizon, then you get quasi-normal modes, and indeed the quasi-normal modes are discrete. The way you see, but when you're trying to quantize a field, you always work in terms of all possible solutions which you then quantize, and the way you then see the quasi-normal modes is as poles in the imaginary axis of the Green's function. So if you use this, if you look at all normal modes and you quantize a field and then you look at the Green's function and then you extend the Green's function along the positive imaginary axis, that guy has poles, and those poles are the positions of these quasi-normal modes. Huh?
The physical Green's function is analytic in the entire complex plane except on the real axis. It's when you continue the physical Green's function from the top part of the imaginary plane through the cut on the real axis, then you get the pole. The poles are not in the physical region.
Okay, so you have, I see. So
that's required for the full, so that the Green's function obey the Lehman spectral representation. So if you don't obey in-boundary condition in the horizon, you get Green's functions that don't obey the Lehman spectral representation, at least on the boundary.
Sorry, you get, sorry, you get what? You get
Green's functions that violate the Lehman spectral representation on the boundary.
If you just, sorry, I don't, if you just try to look at normalizable modes in the bulk, I don't think
anything. Talking about boundary conditions on the horizon.
So let's say you don't impose any boundary conditions in the horizon, you just have normalizable modes. That's what will correspond to physical, if you really quantize a field in ADS about a black hole, then this is what in Lorentzian space would give you really physically Green's functions, I think.
Okay, but if you use the AdS Green's function to get boundary Green functions,
yes,
you will get Green's function on the boundary that don't obey the Lehman spectral representation.
I don't see why. Okay, first of all, I don't know how to understand the Lehman spectral representation theorem about a thermal state. So there's a thermal state, and so there's some.
There's a corresponding statement for thermal states also.
Okay. Sorry. What is the significance of that? Is that these are.
I don't know. I'm very puzzled that you don't have to put the ingoing boundary conditions.
So in general, you don't need to put ingoing boundary conditions if you quantize fields about a black hole. If you just want to quantize a field about a black hole, you work with all possible, because you want to quantize a set of all classical solutions that you have in the Schwarzschild patch. And the set of all classical solutions involves things that go in and things that go out. It's true if you put ingoing boundary conditions at late times, things can be expressed in terms of quasi-normal modes. But even when you quantize things about a flat space Schwarzschild black hole, you consider all possible boundary conditions.
I know very little about quantum gravity in the bulk, and that may well be true. But if you're trying to use quantum gravity in the bulk to get sensible answers on the boundary, I think you'll run into a problem.
I don't, I mean, you can use this. So for example, in AdS3, you can use this to compute boundary Green's functions, and I mean, they're what one expects in 2D theories. But
probably some simple confusion. So go on. Sorry.
Okay. Maybe we can talk later. Yeah. Indeed. So the interior is now. So let's say I want to quantize the theory in in one Schwarzschild patch, And then you can try and quantize the theory in some Kruskal slicing if you like by looking at some eternal thing. You could try and do that. But if you just want to quantize the theory in a Schwarzschild patch, I think you just need to impose regularity. If you look at Birrell and Davies, this is what they will do when they quantize just about a Schwarzschild black hole in flat space. So if you just quantize about a Schwarzschild black hole in flat space, you just look at normal modes. You don't look at, the Hawking calculation is done just by looking at normal modes, not by which impose no condition at the horizon. It just allow both ingoing and outgoing modes at the horizon. We can talk more, but the outgoing, it's true that the outgoing modes in a physical sense vanish because of the Riemann-Lebesgue lemma. They're rapidly fluctuating, so they're not important in some sense. But okay, we can talk more about this. Yeah, sorry, Rajesh, you had something to say.
Anyway, maybe I don't want to belabor this discussion, but you would have, if you didn't impose the ingoing boundary conditions, you would have things with positive, imaginary, whatever. I mean, the opposite.
No imaginary part. I want to look for solutions with real omega. I want to look for solutions with real.
But there would be solutions with. I mean, if you.
So solutions with real omega enough to give me a complete basis of solutions in this thing. I don't want to look at solutions with imaginary omega at all. I want to Fourier transform the Green's functions on the boundary. So I take the Green's functions on the boundary and I just Fourier transform them, and that corresponds to just looking at real omega.
But then a thermal state, if you disturb it, will not be able to relax to.
It will relax because it's still true that these things interfere destructively. So it's true that if you take a thermal state and you turn on some frequencies, if you have a continuous spectrum of this kind, these things interfere destructively, and it's only at some very special point where they interfere constructively that you get this kind of behavior. In fact, it's clear that you have to have this because in the end, there's Poincare recurrence on the boundary. So in the end, you don't have the quasi-normal behavior can't. It's an e to the n square behavior, but it's just I'm just saying that in the end, everything in the boundary can be expressed in terms of real frequencies, which interfere constructively at some point and destructively at some other point.
Yeah, but that you won't see in this perturbation theory about.
You won't see in this perturbation theory, but you can find solutions for real omega in this perturbation theory. You won't see Poincare recurrence in this, and the correspondence of this is just that you take the Green's function and you Fourier transform it in real time. And you think of the Green's function in real time and you Fourier transform that in real time, and that's what I want to get on the boundary. That Fourier transform exists on the boundary. If you take g of x t and I Fourier transform this, then this exists. And it's these modes that I want to get in the bulk. So it's true that yeah, we can discuss more in the discussion section. It's true that at late times this Green's function dies off, but that's not in contradiction with the fact that you have these normalizable solutions. Okay, but we can talk more if okay. Okay. Now the other thing I want to say, how am I doing for time? Probably not very well. Half an hour. Okay, fine. Okay. No, that's fine. I'm doing okay right now. Half an hour is fine. Okay. So let me look at solutions. Where should I look at? Maybe here. Okay. So you get some solutions, and there's one particular linear combination of these solutions that's normalizable at the boundary. So you get these, two linearly independent solutions for chi of z, and you impose one particular condition, one particular combination of those guys is normalizable at the boundary. Okay? However, you can look at how they behave. Okay, how does it behave near z equal to z naught? You can ask how does it behave near z equal to z naught. And the way it behaves near z equal to z naught is that this chi of z, or phi of z, okay, it goes to some e to the I delta into e to the I omega into z star minus t plus k dot x. Star plus t, or maybe I should use minus, put a minus here. I want to keep t positive, but sorry, I'm going to flip signs because I want to keep t positive. Sorry. Some t minus z star. Okay. So you look at the behavior of this field, and there are two kinds of solutions. There are solutions that look like, and this Z star is a so-called tortoise coordinate, okay, which has the property that dz star is equal to dz. Okay, so there's this tortoise coordinate you can define. And in terms of this tortoise coordinate, okay, which has this property, you get solutions that near the boundary, near the horizon, look like this. Okay, so they look like some plane wave solutions. Okay. Now, the fact that these solutions look like plane wave solutions near the horizon, in respect to this tortoise coordinate, actually tells you what's the kind of quantization you need for these fields. Okay. So the way you would quantize these fields is by looking at omega into, so let me call the solution that's normalized in this way, let me call it f hat. Okay. So this delta is some phase shift that you can compute. It's a phase shift that's fixed because there's only a particular linear combination of these solutions that's that's normalizable at the boundary. Okay. And so in terms of that, there's a particular phase shift that you get at the horizon. So it's fixed in principle in that, but you can compute it, for example, in AdS3. I don't know what's the analytic expression higher dimensions, but it's something that's fixed by that boundary condition. Okay. Okay. So this delta is a phase shift factor, and this arises because there's only a particular linear combination of those two solutions that's normalizable at the boundary, and as a result, when you look at that linear combination, specific linear combination near the horizon, you get some such thing. Okay. You get a combination of something that's ingoing plus a combination of something that's outgoing. At the horizon. Now let me call the solution which is normalized in this way. You can of course normalize the solution so as to behave like z to the delta near the boundary with a coefficient of 1, or you can normalize it to behave this way near the horizon. Okay. Let me think of the solution that's normalized to behave this way near the horizon as f hat of omega. Okay. Let me call that f hat of omega. Then this actually tells you what is the kind of quantization you need for this field. And then of course there's a k here. Okay. And I'm not keeping track of 2 pi factors, but let me write them down this time. Okay. So there's a quantization you can do of the field in terms of these solutions of the wave equation that I wrote down, and this quantization can be done in terms of solutions that are normalized. So this f hat has a property that has these boundary conditions. And when I say has this behavior, I mean it has a coefficient of 1. It really goes to a plane wave near the horizon. Okay. So there's a plane wave which looks like t minus z star and a plane wave which looks like t plus z star, and this f hat has this coefficient, has this behavior, the coefficient of 1. That's a normalization. Then I can multiply it with some creation annihilation operators to quantize the field. Okay. And you know already that the kind of commutation relations you now need, these creation annihilation operators have to obey canonical. And the logic behind that is that, let me just try and explain the logic behind that. If you have some solution of the wave equation in some complicated space-time geometry as you have here, and you want to canonically quantize the field. Okay? So in general, if you expand things out in terms of some basis of solutions, it may not be so easy to see what is the commutation relation you need between the creation and annihilation operators. And that's something that could be complicated because that depends on the norm of these solutions that you wrote down. That you have to compute the inner product of these solutions. However, if you know that there's some region of space-time in which these solutions reduce to plane waves, as you do here near the horizon, then in fact that itself, the fact that the field obeys the canonical commutation relations near the horizon, is enough to fix the commutation relations of A omega and its conjugate and its Hermitian conjugate. Okay, so the fact that the field obeys, behaves like a plane wave. Near Z0, enough to tell you that A omega and A omega dagger. I'm not writing K all the time, but have a canonical commutation relation. Okay, with some, yeah. I require what? F hat is unique. So remember I said there were two, you had a second order differential equation for this chi that I wrote down, this radial part. The second order differential equation is restricted, there's only one possible combination of those two solutions that's allowed because you impose normalizability at the boundary. So because you impose normalizability at the boundary, you're now reduced to one linear combination, which you can now scale up or scale down as you like. Okay. Then I further fixed it by demanding that it goes like a plane wave near the horizon, okay, that it has this behavior near the horizon. Okay, now your f hat is uniquely fixed. So first you had 2, you restricted to 1, and then I restricted some 4. I fixed the coefficient also by demanding that it goes like a plane wave near the horizon. Yeah.
By fixing the value of delta and it's a value at the coefficient of z to the power delta at boundary.
Sorry, I've put a boundary condition means what? Sorry, I've just put a normalizable boundary condition. I've killed the non-normalizable mode at the boundary. If you just solve the wave equation, you get a normalizable and non-normalizable solution. I've discarded the non-normalizable solution. So there's one normalizable solution, and that normalizable solution has a particular phase shift at the horizon. And you can scale it up or scale it down. I fixed its coefficient by demanding it goes like a plane wave near the horizon.
Yeah, but the normalizable are the ones which falls off like z to the power delta, right?
At the boundary, this is at the horizon.
Yeah, so once you have a solution, you have to specify the value of delta, like what is the fall off at the boundary.
Right, but that delta is always fixed. You already know that delta in terms of Witten's formula. I mean that delta is given by the usual relation. In fact, that delta in this case is just the dimension of the space. It's just d in AdS d plus 1 because this is a massless field. So that's already known. That we know ahead of time.
But the solution will be different for different values of delta. So
delta is not a parameter. Delta is fixed in terms of the mass of the field that you have in the bulk. So if you give me a field of a particular mass in a particular AdS dimension spacetime, then delta is fixed in terms of that. In this case, when your mass is 0, delta is equal to d in AdS d plus 1. So delta is not a parameter you can alter. It has a fixed behavior.
But from the differential equation perspective, that comes as a boundary condition, right?
From the differential equation, you get a solution that looks like z to the delta, and you get another solution that looks like z to the d minus delta. Okay, so there are two solutions, and the coefficient you get is a1 to the delta plus a2 into z to the d minus delta. I'm discarding the coefficient of z to the d minus delta, which leaves me with one solution, which goes like z to the delta. The fact that the exponent of z is fixed, there's only the coefficient in front which you can choose.
Okay, then how many free parameters do you have to fix to have the you have to fix a value at boundary and then you have to have some condition which will give you a regular solution, right?
So the other condition I chose is that near the horizon it behaves like a plane wave. See, I had two solutions. I got rid of one. I have one solution left. I can pick any linear. I can scale that coefficient, that solution up or down with any coefficient of omega and k, with any function of omega and k. I fix that function of omega and k by demanding that near z equal to z0, it behaves like a plane wave. Okay, so the fact that you have, and the important thing is that the fact that the solution behaves like a plane wave near the horizon tells you what are the commutation relations you need between this. Okay, of course I can. So again, I'm not writing down a k. You can write down a k and then you. So I'll write or not write down a k. I'll be slightly schizophrenic about that. Please excuse me. Okay. Now the question is, what are these coefficients a omega in terms of boundary fields? Okay. So this, that this is how a bulk field has to behave. Okay. And that if you want to write down, you want to extend these boundary values in terms of bulk fields. And the question is that you need some. If you want to write down some bulk operators that give you these right boundary correlators, then you need to be able to find some operators in the boundary that can play the role of these creation annihilation operators. Okay? So that's the question in trying to find out local operators outside the horizon. Okay? Now if you want to find out, so the question is what can play this role. Now one hint actually already comes from the fact that annihilation operators have the property that they factorize at large n. Okay? And that's just a result of the fact that the field you're dealing with is perturbative. Okay? And so as a result, if you think of some correlation function, involving some number of insertions of these guys. So when I write, so I'm going to use sometimes a common symbol for a of so. Okay. So I might sometimes write A of omega and A of omega dagger separately, or I might also write them, you know, in terms of A of minus omega as I've done here to save space. Okay, when I want to say that I can have A omega or of A omega dagger, I might write everything in a uniform notation, in which case this is my notation. This is my relationship between A omega and A omega dagger. You know, if you think of some correlation function, you know, in the black hole, you know that this factorizes at large n. And this is just something very simple. It's simply a statement that if you think of correlators of this field, and you know that 1 over n controls interactions in the bulk, then you know that correlators of this field factorize into products of 2-point functions at large n. Okay? And then there are plus 1 over n corrections. And this is just a statement of the fact that your bulk theory is perturbative. Okay? Now you know clearly that, you know, there is something which plays the same role in the boundary, and these are simply your original fields. Okay? So you know that your O fields that you have now remember that the fields O that we talk about usually, you know, these boundary fields that you talk about, also have the property, if you take a function on the boundary, it factorizes. Okay, this is a bulk statement. And this is a boundary statement. Okay. Okay. So just this gives you a hint as to what are the kinds of modes you need, you know, to play the roles of A omega and O omega. Okay, the kind of modes you need are simply the Fourier transforms of these boundary operators. Okay. So if you just take these boundary operators and you Fourier transform them, okay, then you know that those should be, you know, are well placed to play the role of these A omegas. Okay. I'm motivating this, of course, you know, I'm not giving you a proof, I'm just motivating it. Okay. I'm saying that large n factorization in the bulk and the boundary suggests this kind of equivalence. And of course, and so the claim is that, you know, you want A omega to be proportional to O omega. Okay. When O omega is okay, it's just the mode of the boundary operator. What is this constant of proportionality? You know this constant of proportionality from this commutation relation. Okay? You know that the boundary fields, whatever they are, have some commutation relation. Let me call it G of omega. The reason you know that you have a delta of omega plus omega prime is because correlation functions are time translationary invariant on the boundary. Okay, I'm going slightly fast here, but, you know, just because most of this is motivational. In the end, I'll write down an answer which would be clear to understand. Okay? You know that your boundary fields obey some commutation relation of this kind with the Green's function. That's only a function of omega and a delta function omega and omega prime. And the reason you know that is because correlation functions in the boundary are time translationary independent. Okay? Even if you're in a thermal state, you know, if I compute O of t prime, that only depends on t minus t prime. Okay? As a result, you have some such commutation relation. And that also lets you fix the coefficient of proportionality between this creation operator and annihilation operators in the bulk and in the boundary. Okay? And the claim is simply that you write down A of omega is equal to O of omega by root G of omega. But G of omega is something that you can compute from the boundary. It's the commutator. Okay. Okay. Now let me just take a step back. Okay, let me take a step back and then I'll say what is it that we have done. Let me first of all write O omega here and let me say what it is we've done. Okay. Okay, so what is the result? The result is the following. The result is that, you know, you have some equivalence between boundary operators and between bulk fields, and you have some boundary operator O of omega k. Okay? It has a well-defined commutation relation, you know, with between its modes on the boundary. Okay. You take this O of omega k, you normalize it with the root of that coefficient that appears in that commutation relation, and then you use it to multiply solutions of the wave equation in the bulk that are normalized in the way I explained, f hat. Okay. And this gives you a field in the bulk that has the right properties to play the role of a perturbative bulk local field. Okay, this is the final claim. Okay. Now, okay, so is this claim clear? You know, most of this was just the claim. I motivated the claim by saying that, you know, there was large n factorization on both sides, but you know, you also know that something of this had to be true from the fact that boundary values of correlators of phi are correlators of O. But even if you didn't have that statement, then in some sense this would also tell you in some sense about the emergence of the bulk from the boundary. I don't want to belabor this point, but you know, there are various ways of trying to understand the emergence of the bulk from the boundary, and in fact I think that this is a clear way to understand the emergence of the bulk from the boundary. And the reason for that is that if I just give you these boundary fields O, and you noticed that, you know, by putting them together in this combination with this particular normalization, you would get fields that had the right properties to behave as perturbative fields in a black hole space-time. Okay, then you would guess that, you know, the right description of these fields was also in terms of this dual bulk description. Okay. Now I don't want to talk too much about this emergence perspective. Right now I'm simply making the statement, although I think it's very important and we can talk more in the discussion if you like, that if you give me some boundary fields and I normalize them in this way, and you put them together in this combination, you get some operator that has the right properties to play the role of a local bulk field. Yeah, Rajesh, you had something to say. You had some, yeah.
I can get the corresponding
bulk local operators.
Local operators.
Right.
I mean, now if I want to just check this is, I mean, this construction is correct. What is the precise criteria that this relation has to be satisfied?
Let me, you know, first of all, let me give you one thing you get, which is the consistency check. Let me say it now, in fact. So there's one nice consistency check that you get. So the kind of check you need to make is you need to check if this really obeys the properties of a bulk field. If it does, then you're done. But let me give you a nice, you know, it has to obey some other properties. Let me give you an example of a nice thing that you get for free from this. Okay. So, you know, there's something called the KMS for boundary thermal correlators, which is the following. Think of the following object. Okay. So, you know, we're always going to, okay, so for now we can also view this. Okay. And think of this guy. Beta H of t minus I beta. Okay. You have to be slightly careful about how you do the analytic continuation because the boundary guy has branch cuts. Okay, so you do. Okay. So think of this analytically continued correlation function. Okay. If you're putting this inside a thermal trace, okay, then you know in fact that this is just, you know, trace of beta H into e to the beta H. Zero, okay, which is just trace of e to the minus beta H into O of 0 O of t. Okay. The claim is that if you compute the thermal Green's function with one ordering, okay, O of t and O of 0, and you continue it by minus I beta, okay, by the way there's a branch cut in this, so you continue it by slightly less than minus I beta, you get back the Green's function but with the other ordering. Okay, is this clear? This just follows right now just from the cyclicity of the trace and the fact that, you know, O evolves in this way under time evolution. Okay. And you have to be careful that you don't extend more than beta. If you extend by more than beta, then you get into trouble, so I'm extending by slightly less than beta. Okay, is this clear? This is just a statement about boundary correlators. It's an exact statement, okay, it holds it for all kinds of fields and it holds it at arbitrary coupling. Okay. Now I'm going to show you how this actually gives us something nice about these bulk local fields. You know, you can ask what is the analogous statement in the boundary? Okay, sorry, what is the analogous statement in momentum? And the analogous statement in momentum space is that, you know, if you think of this expectation value, O of omega, O of minus omega, can you call this omega minus omega prime. Okay. Then if you translate this statement into Fourier space, this is just a statement the statement I just wrote, which I erased, is just a statement that P of omega is equal to e to the minus beta omega into P of minus. Okay. So I wrote a I'm sorry, I erased it. I can write it down again. I hope you have it in your notes. Okay. There was a statement I wrote about the analytic continuation of 2-point functions in a thermal trace, and if you translate that statement into momentum space, then the corresponding statement is this. If you define this, this power spectrum to be just P of omega multiplied with the delta function, then the statement is that this is P of W is related to P of minus W with this factor. Okay. Okay. Now this actually gives us something nice. You can ask now in terms of these A of omegas, what is this G of omega and what's the occupancy of this A of omega that you wrote, which is O of omega by root of G of omega. Okay. So you can ask, what is the occupancy of this, okay, in this state in the boundary. Okay. And if you just plug in this relation that is equal to O of omega by root of G of omega, and if you also remember that G of omega is P of W, P of minus W, okay, then you'll automatically get Einstein distribution. Do you want me to do this in detail, or do you see where this comes from? Okay. This comes from the fact that G of omega is just equal to P of W minus P of minus W. Okay. And then if you just write down the fact also is equal to O of W by square root G. Okay. And you look at AW dagger AW, you get a factor of G here, which is where this 1 minus e to the minus beta W comes from, and one factor of PW cancels. So this is telling you something nice. Thermal occupancy of these modes that you wrote down in the bulk is in fact exactly given by the Bose-Einstein distribution. And that's nice. Now that's a check on this construction you did between the boundary and the bulk. You see, the boundary power spectrum can be rather arbitrary as long as it obeys this condition. The boundary power spectrum doesn't have to be this. The boundary power spectrum is something. It could be something complicated, it could depend on the coupling, it could depend on all sorts of things. Okay? But you see that if you define bulk operators, then the occupancy, the number occupancy of these modes is in fact given by some very simple universal expression simply by the KMS condition on the boundary. Okay? So that already is a nice check on this construction that you did between the bulk and the boundary, that you get this universal result. And this is simply telling you that in the black hole background, these guys are thermally occupied, which is exactly what you expect. If you have a big black hole and you have these modes fluctuating about the big black hole, then these modes are thermally occupied. And that's the statement, which is a universal statement that follows from our construction. Yeah, sorry, question. 5 minutes. Oh, 5 minutes. Oh my God, okay. I can make that 5 plus 10, right? Or is it really 5? I can make it 5 plus 10? Okay, fine. Yes, I'll end at 5 plus 10. Okay, sorry, I'm going slower than I thought. I'm now going to spend 15 minutes precisely talking about the interior, and I'll try and limit questions which we can then take at the end, okay? So this is a statement about the general philosophy of how to construct local operators. Now I want to talk about how to construct local operators in the interior. Okay. And there's one key point I want to make. The point I want to make is that to construct interior operators, we need to double the degrees of freedom. Okay, this is a very important point, and I hope if I can get this through, this is significant already. Okay, I'm going to try and explain this point, but this is a point I'd like to get by the end of these 15 minutes. Okay, okay. So what do I mean by this? So let's just to understand this, let's go to, rather than thinking about black holes, I'm going to take a step back and think about Rindler space. Now imagine that you have Rindler space. You take Minkowski space and you divide it up into Rindler space. Okay, so that you have, these are what are called regions 1, 2, 3, and 4. Okay, so you can think of Rindler space. And there's a d-dimensional description of Rindler space, which is that you think of Minkowski space as ds squared equal to minus dt squared plus dz squared plus let me call it. Let me use a different notation, not x. Okay, so x is one direction I've picked out in my Minkowski space coordinate. Okay, you can define some Rindler coordinates. In this region, you can this is the region where and x is greater than mod t. Okay, so you can define some Rindler coordinates. And these are some Rindler coordinates, and the y coordinates just go along for the right. Okay? So you don't have to be in 2 dimensions, you can be in higher dimensions, and that just affects solutions to the wave equation. But the y coordinates just go along for the right. Okay? You can analogically define another Rindler patch here, okay? Except this is the region where t is greater than 0 and t is greater than mod x. Okay? So you can define in region 2, now t minus x is equal to e to the plus xr. Okay, so you can see that this coordinate, the t plus x coordinate, continues smoothly from region 1 to region 2, but there's another coordinate that hits 0 or hits infinity in this language here, and then starts afresh. Okay, if you wanted to extend this, you would have to add an imaginary part to some of these quantities, but otherwise you can just think of these two patches, and you have some coordinates that look like they're the same. Okay, these tr and xr coordinates, but there's some minus sign difference between them, which is important. Okay. Now you can try and ask what happens if you quantize a field in Rindler ADS, and what is the condition? You have a smooth horizon, you have a smooth boundary between region 1 and region 2. Okay? So I'm not doing anything fancy here. I have only Minkowski space. I'm not doing anything more complicated than that. I have Minkowski space which I'm writing in some complicated patches. Okay? And I'm trying to ask that this is just some arbitrary light Minkowski space, and clearly it should be smooth, and there shouldn't be something sitting around at the light cone. And what is the condition that you get smooth correlators across this light cone in terms of these quantum fields? Okay, so I don't have time, but I'll try and indicate quickly what happens. If you solve the wave equation on this side, then once again you get some solutions to the wave equation that near this region, near the boundary between 1 and 2, but on side 1. So let's say you're on side 1 and you're approaching the boundary between 1 and 2 from this side. Okay, then you get some solutions to the wave equation that again have some plane wave behavior. Okay. Tr minus xr e to the I delta minus I delta tr plus xr plus k dot y. Okay, so there's a k which multiplies the other coordinates, but this omega just depends on tr and xr. Okay, so if you're near this boundary, you get some solutions that look like this. Okay? And of course, when you quantize the field, these guys are multiplied by some creation operator, which I'll call a omega. Okay, so there's a bracket here, a omega here. I'm sorry, but it's multiplying this bracket, and you're adding to it the Hermitian conjugate. Okay, so I'm just saying I'm in Rindler space. I solve the wave equation in Rindler space. I go through this process of quantizing things. When I quantize fields, I find that I get the solutions actually are some Bessel functions, but that's okay. There's some Bessel functions. You can expand them in this region when you approach between 1 and 2. Okay, these k Bessel functions. If you expand them in this region between 1 and 2, but on side 1 you find that they have some expansion. Once again, there's some phase shift between these guys, between the left, which is well defined. You can compute it. It's some ratio of gamma functions, and they're multiplied by some creation or annihilation operator, and then you have to add to it the Hermitian conjugate. Okay. Okay, so this is the expansion of the field on this side. Okay. There's of course analogous expansion of the field in region 2. Okay. The analogous expansion of the field in region 2 is that you solve the wave equation again in region 2. This time you get these j Bessel functions. So on this side you get k Bessel functions, on the other side you get j Bessel functions. It's completely unimportant what these Bessel functions are. What's important is that you have some expansion once again in the region. Now again 1 and 2, but on side. So let's say you're now on side 2. Okay. Then on this side you get some expansion, which again looks like, let me call this A omega. And then you have new, okay, which are the other. Okay. So you have some left movers here. And in fact, the left movers are related to the right movers in Rindler space, because the Rindler boundary condition some potential far away at large values of this XR. Okay. And on this side, you have some left movers and right movers. K dot y plus K dot y. Okay. Sum of omega k. Okay. I'm sorry, I'm going a little fast, but is this clear? I hope I'm not losing any of you here.
What's the other boundary condition?
So this is actually, there's just regularity at large x. So you're asking why you get this particular combination between left and right movers, is that the question? It's just regularity at large xr. If you solve the wave equation, you demand regularity at large xr, you get these k Bessel functions and these modified Bessel functions k and I. One of them actually grows at large xr, so you kill that, and that gives you this phase shift. Right, so here you have both solutions. That's why I have A omega and I have A omega. So you have both left movers and you have right movers. You don't, I mean, the regularity doesn't restrict you. You get both independent left and right movers in this region 2. If you went to region 3, once again you'd have one kind of solution. Oh yeah, it should be indeed. Sorry, yes, absolutely, sorry. That's HC. Okay, so I'm not writing down the 2 pi factors and the 1 by root omega factors, but there's an expansion and there are these modes on both sides. Okay. Now you can ask, what is the condition that the 2-point function is regular across the horizon? Okay. What is the condition that the 2-point function is regular across the horizon? In fact, just to make things simple and not worry about this phase shift, I'm going to erase the phase shift from here, okay, and put it here, which I can do because I'm going to put so I'm going to redefine my mode so that the phase shift is not, there's no phase shift in this guy, and there's just a phase shift in the TR minus XR coordinate. I'm sorry, you don't. I'm just doing this just to make the formulas that in the end enter simple. Okay. Now why do you want 2-point correlator? Because this is just Minkowski space. This is just some arbitrary light cone I drew in Minkowski space. There's no reason the 2-point correlators across here should not be regular. It's just Minkowski space. Huh? So the field itself should be continuous, and demanding that the 2-point function is regular and has the right short distance behavior, in fact, is equivalent. It's stronger than demanding that the field is continuous. Okay. So now you demand that phi of xi, phi of x1, and phi of x2, okay, that has the right short distance behavior as x1 goes to x2. Okay. Very nice paper by Candelas from 19. Which does this for a black hole. Let me see if I have the reference here. Yeah, so it's called vacuum polarization in Schwarzschild space-time. It's from 1979, okay, which basically does this analysis, not quite in this, and it does it about a black hole. Okay, but it's kind of nice to read for this kind of analysis. Okay, it does it about a Schwarzschild black hole, but it's really the same analysis. Okay, so you can ask that you look at this correlation function, it should be regular. In fact, it should have the right behavior, across this horizon. It shouldn't just be smooth. It really needs to have some well-defined short distance singularities. Okay, it should go like 1 by 1 minus x1 minus x2 to some power. It has to have the right behavior. And if you demand that it has the right behavior, you find 2 kinds of conditions. One of them is that A omega, okay, What do you mean? How do you calculate this? You have an expansion, right? So you have an expansion for the field both in region 1 and in region 2, right? So this correlator you get in terms, so the whole field is sitting in some state. This state is the Minkowski vacuum. Okay? So you can okay. So when you compute this 2-point function, you get an expression in terms of 2-point functions of a omega with that small a omega and b omega with that small a omega, okay, in the Minkowski vacuum. So this this 2-point function gives you conditions on what the or if you compute n-point function, it gives you conditions on what the n-point functions of a involving a, capital B, capital A, B and small a have to be in the Minkowski vacuum. Right, but now I gave you an expansion for fields in both patches, right? Okay, so let's say you compute a correlator, not just involving 2 points, but involving many points. Okay, let's say involving 2 points. You agree that you can relate this into correlators of the following form. With some coefficient, right? Just from the expansion, because you know what phi is in one patch and you know what phi is in the other patch. So if you just expand this out, it gives you correlations of small a omega with capital A omega and B. And you can do the same. You don't have to only look at 2-point functions. Okay, sorry, I'll end soon. Sorry, the chair is getting nervous. Yeah, okay. Just a few minutes more, almost at the end. We can talk more about this. Okay, the statement is just that given the expansion of the field in region 2 and given the expansion in region 1, and demanding the regularity not only of 2-point functions but of higher point functions, gives you a constraint on what these correlators have to be. Okay, in the Minkowski vacuum. Okay, in fact, you can already see that the correlators of a omega and capital A omega have to be. Okay. Okay. So you see already what a omega has to be. You see a omega is multiplying this t plus x. Okay, so these are the left movers in this side, capital omega and small a omega. Okay. Both of these are multiplying left movers on this side. So left movers from here continue smoothly onto this. Okay. So left movers continue smoothly. That means that within correlation functions, okay, at least within correlation functions, or really even to get continuity of the field, as someone said, I should say A omega equal to capital A omega. Okay, this comes from continuity of the field. Okay, this is just a statement that left movers continue smoothly. Okay, it can't be that the correlation between A and B is 0. If it was 0, that wouldn't have the right form to be a correlator in a vacuum Minkowski spacetime. Okay? Because the vacuum Minkowski correlator involves also cross correlators of this kind. Okay? And so the next statement that you get is that whatever the Minkowski vacuum is, it has the following property. Okay? It has the property that B omega on the Minkowski vacuum looks like e to the minus pi w into a omega. Remember the a omega I wrote in region 1 on the Minkowski vacuum. Okay. Okay. So you require these two properties for the horizon to be smooth. Okay. If you think of the second property, it's, b omegas are independent modes. So it's true that b omega and a omega is equal to 0. These are not the same modes. Yet this state in some sense is an entangled state, so that the action of b omega on this state can be written as the action of a omega dagger. This is a omega dagger on the same state with the coefficient up front. Okay. What is this a statement of? This is simply the well-known statement. If you think of where these b omega modes come from, remember I said a omega is equal to a omega, which is a statement that left movers continue smoothly. I could also have done a quantization of the field in region 3. In terms of some fields on this side and some creation annihilation operators on this side. And then these b omega modes that I wrote down there would actually match up smoothly to right movers in region 3. Right? And we know there's a famous statement, you know that the Minkowski vacuum, you know how it looks like in terms of the Rindler vacuum. The Minkowski vacuum, in fact, looks like this. A omega dagger in region 1. So let's say I call these guys A twiddle. Okay, so the creation annihilation operators in region 3 are this, and you know that the Minkowski vacuum has this famous form. So the Minkowski vacuum is an entangled state between states in region 1 and region 3, and it has this form. Okay. If you plug in this form and you set the fact that B omega is equal to A tilde omega, then you find that this will follow. Is this clear? Okay. So this statement is simply the same as this statement. It's simply a statement that the Minkowski vacuum is this entangled state of guys from region 1 and region 3, and these B omegas are actually coming from region 3. Okay. But you need these conditions independently of this physical intuition of why this happens. You need these conditions in order to get a smooth correlator, a smooth, across the horizon here. Okay. So you need these conditions just independently, and you know why they are true. Okay. If you were to distort the Minkowski vacuum by some huge amount, by exciting lots and lots of modes so that this relation was not true for many modes, then you would not get a smooth correlator, and that's what would be a firewall where this condition is not true. Okay, I see the chair is getting very edgy, so I'll stop here and continue next time with the implication.